Welcome to the lecture on analysis of RTD curves. So, in the past lectures we talked about different aspects during the physical modeling. So, how we have seen that the tracer is injected, then you have to draw these using the stimulus response techniques. So, you have to draw to trace the concentration, maybe in the pulse manner the tracer is added, or it may be added in the step manner. So, by that you are getting the RTD curve, and we must understand try to understand that how these RTD curves are to be understood. So, what does it signify? Especially we will talk about finding the mean residence time, then also the mean and variance of these residence time. So, from these RTD curves. So, that is what our aim will be in this lecture. So, what we saw, so once you get the RTD curve. So, you have to get the mean of the RTD curve, and the mean of the RTD curve. So, that can be found by the expression. So, that you will be writing as T mean. So, T mean will be integral of 0 to infinity T c dt, and it will be divided by integral 0 to infinity c dt. So, as you know that you are having on the abscissa, you have the time axis, on the ordinate you have the concentration axis. So, as with time, so you will have this T c dt and divided by c dt. So, if you can see the analyze even by dimension wise, it will be something in terms of time. So, this time basically will be known as the T mean. So, mean residence time. Then if the concentration is measured in the equal time intervals. So, if concentration is measured in equal time intervals. Now, in that case you will have equal time interval of delta t. So, that is of delta t. In that case you will have to have the expression for the T mean, and this T mean in that case will be summation of T I C I delta t. So, that will be summation, and that will be divided by again C I delta t. So, it will be C I delta t. So, if the equal time interval is there, that is delta t, in that case that will cancel. So, it will be summation of T I C I and divided by summation of C I. So, this is going to tell you this by this. So, once you have these concentration data with time, then we can find the mean residence time inside the Tundis. So, that is done by this formula. You can find the variance of this quantity. So, this variance, so that will be statistical variance. So, that talks about the spread spread of this residence time about the mean. So, so that variance is calculated, that is spread of the residence time distribution about the mean. So, that is found by sigma t square. So, as we know, we have to take the difference of the individual value with the mean value, and then it taking the square, and then further you are taking the we are further taking the ratio. So, that will be 0 to infinity, and then you have in this case you have t minus t mean. So, t mean what you calculate, using the earlier expression. So, that will be square and then c dt, and that will be divided by integral of 0 to infinity c dt. So, this way you calculate the variance of the residence time distribution about the mean. Now, here also if you have the equal time interval, so for concentration measurement at equal time interval, so in that case again you give the term delta t. So that will be sigma t square, it will be again summation over I. So, that will be T I minus T mean. So, that will be squared, and then you have C I into delta t, and that will be divided by again summation over I, that is C I delta t. So, that way as delta t is equal, so that will be anyway cancelled. So, it will be summation of T I square C I over summation of C I, that is I. So, that is what we have seen. So, this is T mean, and this is your so that was mean time, and in this case you have this as the variance that is computed here. So, that way you have the square term, and this way you compute these mean and variance of the Rtd curve when you get these values experimentally or by any other means like simulation or so. Then if you are talking about the C curve, so in the case of C curve, so from C curve, so in that you will have the dimensionless mean of residence time distribution. So, you can calculate the dimensionless mean of residence time distribution. So, in that case you have dimensionless term which will be coming into picture. So, that will be defined by theta bar, and that you will be calculating as 0 to infinity theta c d theta, and that will be divided by 0 to infinity c d theta. So, same way in that case you have c dt, and here you have capital C. So, that is your dimensionless term. So, then you calculate it as c theta d theta. So, that will be the dimensionless mean. Similarly, you have the calculation of the variance. So, dimensionless variance So, dimensionless variance basically will be again based on the relation. So, that will be sigma square. So, it will be 0 to infinity, and it will be theta minus theta bar, that is the dimensionless mean value. So, it is a square term and then c d theta, and that will be divided by c d theta. So, this will be 0 to infinity. So, that is for the continuous function. Now, if you take for the equal time interval, so for measurement at equal time interval, so in that case your equation will be like you have theta bar. So, that so that will be summation of c I theta I. So, that will be summation over I, and that will be summation of c I. So, that way you will have the theta bar is theta average, and similarly you will have the variance. So, that will be theta I square C I, and that will be summation of C I, and then we are going to have the subtraction of theta bar square. So, this way we calculate these mean as well as the variance quantities in the case of the RTD curves. So, we can understand it using one example. So, suppose you have one example where there is concentration measurement. So, that you can understand using that example. So, the concentration readings are plotted for continuous response to a pulse input into a closed vessel. So, for that one which is used as a chemical reactor. So, for that there are readings, and you will have the reading of the concentration at different times. So, you have time t, that is in minutes, and then you have the tracer output that is given. So, there is a tracer output concentration, that is C pulse, that is in the term of gram per liter fluid. So, suppose you have the values which are given to you. So, suppose at you are taking at interval of 5 minutes, so 0, 5, 10, 15, 20, 25, 30 and 35. So, suppose this way you are monitoring these tracer output concentration at these times, and the values which you are getting is at 0 it is 0, then you have 3, 5, 5, then you have 4, 2, 1 and 0. So, this way suppose your concentration readings are coming when you are measuring it. So, there are many measuring devices. You have conductivity meters are there by which you can measure, and there are many data stick is there. So, there are many devices which are used for measuring these output concentration. So, you can find the mean residence time. So, the mean residence time so that will be T bar. So, it will be you have as you know that you have the delta T of 5 minutes. So, you have summation of T I C I delta T I and summation of C I and delta T I. So, as delta T is constant, so you will be writing as summation of T I C I, and that will be summation of T I C I, and then that will be by the ratio of summation of C I. So, you will be multiplying these, and then you will be adding. So, if you add, so that way T I C I, so you are adding, so that will be first will be 0, then you have 15 plus, so you will have 0 plus 15, so that is 15, then you have 50, then you have 75, 80, then you have 50 plus 30. So, this is coming, and then you have 0, and if you add the concentration, so that is TICI, and then you are having the concentration summation. So, that is 3 plus 5 plus 5 plus 4. So, this will be 3 plus 5 plus 5 plus 4 plus 2 plus 1. So, it will be 65 plus 75 140, 220, 270, and this is 300. and if this is 13 for 17, so this is 300 by 20. So you are getting the value of 15. So 15 minute is the mean residence time. That's what you are calculating. This 15-minute time is the mean residence time when you have such are the readings. So 15-minute will be the mean residence time. Now what we see in this case, normally you also can find the variance of also the mean residence time. Variance about the means, variance of the RTD curves can be drawn in this case. And also you can plot the RTD. So you have at 0 it is 0, then at 5 you will have 3. So you can have that value also, and what you see that you will get some similar kind of curve you will be getting. So at the different times you will have the values coming, and this way you can have the value of you can have the plot of the RTD curve. So depending upon, so what happens that when you do the experiment, in that case you have you can either you can measure manually, or you have you can connect it with the computer, you get the readings. These readings are basically stored in computer, so you can have it in stored in Excel or in any graph plotting software, and then from there you can draw the curves. So that's how you draw. So you can further calculate the variance over this. So you know the mean, then you will be taking the difference of the value from the mean. So that way, and accordingly you can have the calculation of variance also. Then we will talk about the other model, which is a conceptual model, and that is also used for the analysis of these response techniques. So that is that is known as the tank in series model. So many a times we feel that it's like tanks which are which are the where the mixing is taking place, and they are connected in series. So in that case the response of the tracer, which is there at the different places, so that how that response will be coming, how they will be responding to the changes in the concentration. So that is to be seen. So if you talk about this tank in series model, so your tank in series model is there. Now in that case what we talked is that you can have the tanks connected in series, and you have these tanks as the well mixed tanks. So they will be giving the they will be giving the tracer responses, and they are similar to that is given by the dispersion model. So any type of such model can be used to correlate the experimental data which is obtained. So you will have some model results, and then you will see that from the experiments also you get that kind of RTD curves when you have the outlets which are far away. So when you have a vessel where the input is coming at one place, and then you have different places where you have to measure the output. So it's like it's like the tanks which are connected in series. So in those that numbered tank, you will have the tracer response in a different manner. So, if you recall, for one tank, so this is the, if you recall that if you go for the C curve, so C curve for one well mixed tank. So, as you know that you recall that the for the well mixed flow, the exponential that curve was seen. So, in that case that will be represented by C equal to e raised to the power minus theta. Similarly, if you have n well mixed tank and they are in series connected together. So, for the for those n well mixed tanks, in series. So, for those n well tanks in series, so C curve again will be given by the equation. So, for that you have C equal to n raised to the power n theta raised to the power n minus 1 e raised to the power minus n theta divided by n minus 1 factorial. So, this is for when you have n well mixed tanks in series, you can predict the value of the concentration according to this. So, and if you take the variance of these curves, so variance of the curves if you determine, it will be 1 by n. So, these experimental data which you get, and you have the theoretical C curve. So, you both can be matched, and your results can be validated for the different tanks. So, and can be even, as I said, that and maybe even a non-integer also. So, this is one parameter model, and here the parameter is that the number of tanks. So, based on that n. Now, if you go for the large number of n, so if you take a C equal to 1, it will lead to the same value. If you take C as n as 1, if you take n as 2, so it will have a different value. What we see that as you go, as you increase the value of n, so as the value of n is increasing, so it becomes more and more symmetrical in shape. So, it has it is found that for a large number of tanks, that is n, so C curves become increasingly symmetrical. So, if you see the first curve will be like exponential 1. So, it will be starting from 1 and it will go for well mixed flow, but as the n is increasing, so that tends to be more and more symmetrical. So, that can be seen, and for the closed vessel, if you try to see that if you that can be understood by having the analysis of these plots. So, what is seen is that if you have C as this, and if you have theta on this line, so for n equal to 1 it will go like this. So, this is for n equal to 1. Now, the thing is that if you have n equal to 2, so that will move like this. Similarly, if you have for example, if you have n equal to 6, so it may go like this, and if you have n equal to 20, so it will move like this. So, this is n equal to 2, this is equal to 6, this is n equal to 20. So, this has been reported in the literature. So, what happens that if you see this when it is n equal to 1, this is basically this is how it starts from here, that is 1, and you have 0.5, and then this will go as 1.5. Similarly, you have theta as somewhere 1 here, and then you will have this side you have 0.5 and this side you have 1.5 or so. Now, this both these tank and series model, as well as we have studied about the dispersion models, where we have got the expression for the for C. So, depending upon the values, dispersion numbers and all that, d by UL and all. If you compare, so if you see both these models, they give rise to similar type of curve, that is C curve. And if you compare these two models, so you can have, after comparison you can see that you will get 1 by n will be 2 into dE by UL. So, that is your dispersion, vessel dispersion number, minus 2 into dE by UL raised to the power minus 2, and then you have in bracket it will be coming 1 minus exponential minus of UL by dE. So, this is how you for the closed vessel. So, this is for closed vessel, this is the correlation which is which is coming once you compare, once you take into consideration the models of the tank and series model, tank in series, and all these other dispersion models. So, and that also, so we will also see that how these what these indicate. So, basically when you have connected in series, when your tanks are basically connected in series, so basically you have this is the first tank. So, you will have this tank here. So, this is having mixing here, and this is mixing, then it is connected to the second tank. So, here again this is also rotating. So, you will have first, this will have second. So, that way you will have the third one. So, all these are connecting, and then that way it will go to the nth tank. So, you will have n tank which is connected in series, and so if you see that for this tank here the mixing is more. So, mixing has dispersion is more. So, it starts from here. However, if you go to this tank, so in this tank it has started, it has gone like this. For the third one it will be delayed from here, and it will go on delaying as you go towards the larger value of n. So, that is indicative of the other things also, like you have different regions. If you see here you have completely well mixed zone starting, whereas if you go to the other regions, so in this there is no dispersion. So, you have a certain component like the plug component. So, you have mixed component as well as plug component. So, those things they can be analyzed using these curves, and they have certain meaning. So, as you move you see that it is getting delayed. So, this plug part is getting apparent here, whereas in this part plug part is not seen, because here is pure mixing, I mean well mixed flow is more prominent in this case. So, that way you can have the analysis of the curves in different manners. So, we will talk about the other models also. You have the combined or mixed models. So, with that model also we can analyze these RTD curves, and in the coming lecture we will talk about the analysis of these RTD curves for by taking into account the different zones inside the Tundish. So, you will have so this way you are seeing the plug zone. So you will have the mixed zone, and similarly you will have dead zone. So all these things will be discussed as we so we will have another apart from this Rankine series model, also you have combined models. So that we will discuss in our coming lectures. Thank you very much.